I'm just Ladyada.
Hey everybody, and welcome to my desk. Happy Sunday. Got my haircut done, so it's nice and cooler for the summer because it's nice and toasty out. We've been doing a little bit of hardware. I did actually a lot of tester repair this week, and some other stuff in prep for the move, but I did get a little bit of hardware done. So let's go to the overhead and we'll show what I got ready for this week. So I wanted to put the DS2484 boards in stock, hopefully next week or the week after. This is that I2C to one wire converter board, which I think will be really useful for single board computers. If they can run bringup, they can then add one wire. So the way the tester works, I have a DS18B20 here and all the pogo pins, and so the sensor itself connects as if it was plugged in directly to the terminal block, and then you can see it beeps and blinks. It does a I2C. It basically uses the library I wrote to do an I2C, a one wire search, find all the devices connected, and then read the temperature. And as long as it can find at least, the one DS18B20 and temperature, is good to go. So this test is nice and fast. Looking forward to getting these tested next week by the fab department. And then we can get these ready to be stocked and in the store. So that's going to be cool. Another thing I worked on this week and is the Adalogger RP2040 board. So I think I showed this off like a week or two ago, or the design. So it's the Bones board that I've been, modifying and making multiple different styles of. I've got one with like a LoRa module. I've got one with a USB host. I've got one with a DVI output. And this one, I just stuck, our standard micro SD card socket in, and I connected the pins both with SDIO and SPI, even though we don't have SDIO support. And I looked a little bit today into SDIO support in Arduino, and I found a couple platform IO libraries, but they don't use the Philhauer core, they use embed. It's got like very hairy and complicated, and I think it actually might be better if we just try adding SDIO support into CircuitPython, although it also looked like SDFAT beta, which is Phil Grayman's library for interfacing with SD cards that we use a lot. It's a really good library because it has like long file name support, supports like exFAT and stuff. He's added some PIO interfacing for SDIO in some version, but it hasn't been released yet. Anyways, it's like you kind of end up in this rabbit hole. But I didn't want to get SPI tested, and also, of course, I2C. And then what I'm going to do is write a demo that just logs temperature and humidity, maybe from a real-time clock. Also, I'll have like an RTC and this temperature humidity sensor, and I'll log it to the SD card. Let's go to the computer. I'll just show the schematic really fast. So one of the things I tried to I'm trying to do a better job with every design. So having very light pull-ups on all of the data pins should make, one of the issues we have with SD cards is, I think if the pins are floating and then you insert the cards, like the pins jiggle a little bit, and you can maybe accidentally put an SD card into SDIO mode, and then it's very hard to get out of SDIO mode because it initially boots in SPI mode, and then when you send like certain data, you can put it into 4-bit SDIO interface. But like again, like 99% of people don't want to do that. They want to use SPI. And so having these 47K light pull-ups, I just used some 2 resistors and then a quad resistor network. And then wiring up the SD card, because I have these 8 pins in a row that are available. Like the thing about the Bones board is I left these pins unused. Like every other pin got used for like, the UART and analog inputs, and the GPIOs, I wanted them to line up. So GPIO 4 is D4 and GPIO 6 is D6. So it's because there's no remapping in RP2040. Like there is on like the SAMD21 or the NRF52840. But so we have these 8 pins in a row, and this was great for like the NeoPixelate board, Scorpio board, because you had, if you have 8 pins in a row, you can do PIO that is parallel, because oftentimes you have to have the pins in a certain order in order to do like multi-bit writes in at the same time. So for this one, because I have only the SD card slot, looking up the, actually now I think about, I should look up the 2040 SPI. Yes, this is like my favorite is when I find the thing that I already did. Okay. So, you could look at the different GPIO. So GPIO 16 through, goodness, it's 16 through 23. And, well, 23 isn't here, but you can see that some, not all of them can do SPI. And so the trick is, first off, the SPI port, we already have an SPI port. That's like the main port, and that's SPI 0. So we want to use the second SPI port, SPI 1, for interfacing with this SD card. But at the same time, we want to leave the possibility that if people want to do SDIO interfacing, they can. And for SDIO, you have these 4 bits, data 0 through 3, and you have to read and write them in parallel. And so they need to be in order, but at the same time, like, not only do they have to be in order, but then the pins that are shared with SPI have to also match. So luckily there is like one mapping that does work where we do, put this to the side, put this to the side. So pin 18, GPIO 18 is SCK1. So that's the clock pin. And then the MOSI pin is on 19, which is DO0. And then MISO is on DI0, which is GPIO 20. And then we use DAT1, DAT2, DAT3, and then the CS pin can be on any pin. So it turns out to like that works out. And then because we have like 3 pins after DAT0, like it just works out. You can have 4 pins in a row for the data lines. And then these 2 pins, 16 and 17, they're extras. We end up using those for the card detect and the NeoPixel. So actually I lied. The initial, the feather SCK pin is on 14, which is SPI 1. So underneath here. Yeah, so SPI 1 is the main feather SPIO port, and then SPI 0 is the one for the SD card. And yeah, I mean, I'll chat with CircuitPython team if they're up for like adding SDIO support. I think it'd be cool, but like, I don't know, it is possible to do, and there's example code, but like I said, it's only for platform IO. It's using the SCSI converter. So the good news is I wrote like a really quick example for this. So let me eject the SD card. It says SD card removed, and when I plug in the SD card, you see it detects and then it prints out, yes, here's all the files. So now I know SPI works and the SD card detect works. NeoPixel I know works because, when I boot CircuitPython, it blinks, and then I test all the other GPIO. So basically this board is like ready to go and done. So I'm going to order the PCBs and we'll get them into the shop. So that's pretty cool. I think it'll be kind of popular. People really like the Adalogger boards. Okay, how are we doing on time?
Good, you're up to 10 minutes.
Okay. Let's so the next thing I was doing is I got like a random request on the forums to, we've been doing a lot of infrared interfaces. So we did this code learning IR board, and then I did like an IR receiver and an IR transmitter. I don't know if it was long enough ago that it's already off the front page. Hold on. Yeah, I did this one. Yeah, here the TS demodulator. And then I also had the receivers. So it was like the Transmitter. Yeah, this is the like generic receiver board. And then we did the infrared emitter, which you would modulate. So we got like the two-way emitter. So this is good for infrared remotes, but another thing that infrared used to be used for was transmitting and receiving data from like smartwatches and PDAs using a protocol called IrDA for like infrared data. Hold on, I'll break out IrDA protocol. Yeah, infrared data association. I mean, this stuff is like so 90s. So like in the late 90s, early 2000s, laptops and PDAs, you could, if you didn't want to have a gigantic serial port because USB wasn't really popular yet. I mean, it was popular, but it wasn't like universal. And then, although it has universal in the name, and Bluetooth definitely was not being picked up yet. It was very, very early. And Wi-Fi, of course, was extremely expensive and power hungry. So RDA was a kind of a cute idea, is that you'd put your device next to your laptop and it would beam data back and forth. They call it beaming, and it would be good for like half a meter to a meter. On one hand, it's like this could be good for like retro interfacing and stuff. But there is I could see a use case for like some macro projects where you want to transmit data. First off, I think you might be able to do one-to-many because it's like it's just sending data. Maybe you can have multiple receivers, although there might be some sort of a link protocol underneath. And but still, if you have two devices and you want them to communicate and you don't want to like have the expense and complexity of an RF protocol, they don't have Bluetooth, and maybe you don't want to deal with a Bluetooth stack. You don't want to do Wi-Fi because it's high power. IrDA could be not so bad. It can go as fast as like 115.2 kilobits. So it's like UART speed. And even kind of looks a little bit like a UART. And so I've been learning, like, I haven't actually looked at RDA in like 20 years. So I'm kind of like relearning this stuff. But I think it would be kind of cool to have a little, like maybe a little breakout boards where people could like send data back and forth using IrDA. Because you could just use your hardware UART instead of like a whole stack. Like you'd use the built-in serial port, which also means you could communicate from a computer wirelessly to a device, again, without like a Bluetooth stack or like RF interfacing. So let's go to the great search. Let's find an IrDA transceiver.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Thanks, DigiKey. Every week, Ladyada uses her powers of engineering to help you find the things on digikey.com. Ladyada, what are you looking for this week?
Okay. So this week I've become interested in IrDA. So let's go to the computer. I just chatted about it, but since it's a split video, I'll kind of run through it again. To 90s, 2000, pre-Bluetooth, pre-USB universality protocol where you could beam data between like a smartwatch and a PDA or two laptops or like, like a gadget, like a lot of gadgets you could transmit back and forth. And it used infrared light. By the way, people in the 90s, I mean, even now, people just love IR. Like, it's so great because it's like you can transmit data, you don't need certifications, it's safe for the eyes, it's not like a laser, and you don't need like antennas. It's fairly low power because you just need an LED, and it's low distance, which is good. It's like you don't have to worry about people like snagging your data. I think I vaguely remember these were called PANs, like personal area network, because it was like 1 meter. We had WANs and LANs, and then PANs. I don't know. It was the 90s. We also had gigantic pants. Okay. So IrDA is interesting. You do need to have a hardware layer there's a couple different layers, it turns out. There's like the PHY, there's the low level, like how do you actually transmit the IR back and forth and modulate it. And then there's layers above that that eventually do get you UART like baud data, like a COM port or a serial port or a hardware UART. So let's start by getting the transceiver. So you can go on and on. There used to be a lot of these, and I actually wasn't even sure that you could still get IrDA transceiver, but let's try. So IrDA. Let's just search for IrDA. Okay, so we search for IrDA. So unfortunately, IrDA is it's you're probably going to find stuff that has it as a sub string, but they do have a whole section of the catalog for IrDA transceivers. So let's check it out. So the good news is there is stuff and it's in stock. However, one thing I definitely noticed is there are a lot of stuff that isn't in stock. I think a lot of companies, Sharp, Sharp is famous for their IR stuff. Zilog, Light On, they all made infrared transceivers for IrDA, but not really. So we only want to look at active, and you can see it goes from like 140 down to 16. A very big reduction. Another thing I noticed, which I didn't realize, is there's multiple standards for the phi layer, the physical layer, which actually designed a breakout board and then realized, already started looking at this earlier in the week and then realized like, oh, there's actually multiple layers. If we look at this, so there's the fire layer, which identifies and talks to things. I'll say if you're communicating with like retro tech, chances are I think you'd probably be fine even if you didn't have the latest phi. But it's interesting to note that if you want the highest distance link range, well, first off, let's only look for stuff that's normally stocking, because like if it's not even going to be available, because again, there's nobody's making new IrDA chips. These are just things that are left over. If you want 1 meter range, it looks like there was only, if you look on the right, IR-Phi 1, 2, 0, and 2. So at the 1 meter range, if you want the latest Phi version, which another thing that's nice about this is it runs at 5 volts. It's 2.7 to 5 volts. The TFBS 14711, and there's a lot of these in stock, and so these look quite promising. There's not quite sure why there's like a 3 version, but the TFBS seems to be pretty popular, and I like that it can do 1 meter. And it's pretty simple. So you you wire up, it has the built-in LED, it has a receiver. You read and write RxD and TXD data from it, and you can also put it into shutdown mode if you want low power. So like you don't have to worry about finding stuff. And like I said, it's 5 volt friendly. One thing I didn't realize until I sort of looked at this and I did a quick breakout design just to kind of get the rough layout and pinout working. And also I want all the extra resistors and capacitors. After I designed this, and I was like, oh, I should probably read the rest of the data sheet. So even though this says RX and TX, it's not UART. That the module itself is not UART. You need to get a separate modulator that takes UART data, like 8-bit high, low, and converts it into the IrDA protocol that uses the phi that's created by this IrDA module. What I'm saying is you can't just like connect your microcontroller RX and TX to this this transceiver and expect it to work, especially if you're communicating with other IrDA devices that like already exist. Although you might be able to just like kind of, if you're just doing point to point, you might get something working. What they want you to do is get a separate, I think of RP2040, like, Pico could probably do it with PIO because you probably need to like do some encoding stuff. You probably like, have bit stuffing and like minimum maximum bit widths. But you also need the TIR 1000, which I looked up, and this is a UART converter to the infrared transceiver. So with this one, you have the IRTX and RX, and then the UART, RX, and TX, and so it does the pass through. However, you also need the 16-time clock input. So like as I start looking at this, I'm like, oh my god, it's getting a little complicated. And the clock signal has to be 16 times the baud rate. So, you know, you could generate this or alternatively have an onboard crystal. So I have to kind of actually go back to my simple design that I did. And while this is all cool and all, I have to extend it to add this extra chip that'll let you actually communicate with IrDA using UART. So while this is my, I'll get to this in a second. Hold on. You also want the separate chip. So there's the TIR1000. Oops. Which thankfully is stocked at DigiKey, and they have lots of them. Basically just different, they're all the same chip, but just some are TSOP and some are SOIC. You can pick whichever one you want. They all seem to be in stock, and they're about like $1. Maybe this one looks like there's a lot in the marketplace. So, and it's not discontinued. Or you can use the, is it the MCP 2022? Sorry, MCP 2122. Pardon me. Which is also available. They even have a dip version, which just goes to show how long Longos must have been created. But they do have, you know, 16,000, the MCP 2122. There's probably some, like, there's a lot of probably industry, maybe like medical, maybe business, maybe like interfacing with older devices, IrDA transceiver work. So these chips are still available. And these ones are also, you know, about $1.80. So like I said, you'll need both of these in order to actually do UART to IrDA transceiving. But if we're going to pick one, you know, can start with this. The TFVS4711 comes in TT, which is up, and TR, right angle, like same chip, but one points up and one points to the side. Pick which one. Just want to start, and then again match it up with either that TIR1000 or the MCP 2122. Bob your uncle, you can do UART to baud rate. UART at up to 115.2 kilobit per second baud rate to IrDA transceiving, so you can communicate with your old, I don't know, GameCube controller, Palm Pilot 3, all sorts of stuff. It's my pick for the week.
Where in the world is that part I need? The great search with DigiKey.
All right, that's our show. Thanks so much, everyone, for joining us. We will see you throughout the week for a variety of shows and more. Stay tuned to Adafruit.com.
Bye, everybody. Have a great week.